Welcome to lecture number 9 for ECE 321 Analog Electronics. Today's lecture is about Butterworth, Elliptic, and Chebyshev filters. Now, the objective of this lecture is to explain what is a Butterworth, Elliptic, and Chebyshev filter. After this lecture, you should know how these filters compare. And the types of filters we're looking at are RC, Butterworth, Chebyshev, and Elliptic. Chebyshev is also called a type 1 Chebyshev. Elliptic is called a type 2 Chebyshev. Other names for them. So starting out, the simplest filter you can build is probably the RC filter. This is a filter that has n poles. All the poles have to be real. There are no zeros, and the maximum gain is 1. This is called an RC filter because you can implement it with just an RC circuit. Basically, an n-poled RC filter has n poles on the real axis, n capacitors, and n resistors. Its advantage is you can build it just with resistors and capacitors. That's good. The problem is it's a really lousy filter. So, to give an example, suppose I want to have an RC filter where the corner is at 10 radians per second, and I have n poles. This would be the transfer function of it. The DC gain's 1, corner's at 10. If you plug in S equals j omega and you calculate the gain versus frequency, here's what it looks like. The gain's a maximum at DC at 1. The corner, ideally, the gain versus frequency is 1 at 10 radians per second, then drops off. That's kind of what the corner means. It's not very ideal. The gain isn't flat at 10 radians per second. Immediately the gain starts dropping off. That's for one stage. Two stage, the gain is that squared, cubed to the 4th to the 5th power. So it doesn't really pass the frequencies between 0 and 10 all that well. So it's not a great filter. That's about all you can do if you're going to limit yourself to having real poles. The plus side of an RC filter is I can build it just with resistors, capacitors. To prevent loading, what I'm going to do is each stage, I'm going to increase R by 10 times. So 100 goes to 1K, 10K, 100K. That doesn't eliminate the loading, but it makes it smaller. It's like 10% loading. Whatever this current is, only 10% goes through the 1K. If you do that, then each stage, 1 over RC equals 10. So that's 10, this is 10, that's 10. Doing that, you have, in this case, a 5-stage RC filter. Again, where the gain versus frequency isn't great. It is a low-pass filter. Gain versus frequency is this curve right here. But really, that's about all you can do with the real poles. If you throw this in Circuit Lab, you can build a filter and sweep. What I would do is, if the input is V0, I would sweep the frequency of V0 and plot the gain of the last stage. And here I plotted it on a linear scale rather than a log scale. If you do that, you kind of see that the gain is 1 out to, well, in this case the corner is at 1 radian per second. Gain drops off right away. Not a great filter. That's an RC filter. Butterworth filter is the closest approximation to an ideal low-pass filter, subject to the constraint that you have n poles, there are no zeros, and the maximum gain cannot exceed 1. So what that means is if I plot the gain versus frequency, here's frequency, here's gain. This is what I want. I want the gain to be 1 out, in this case the corner is at 1 radian per second, because 1's a nice number. I'm not allowed to make the gain go bigger than 1. The nice thing about Butterworth filters is there's only one of them, so these are nice for midterms. If I create a midterm, I'd like there to be only one answer. They're actually pretty easy to calculate as well. The idea of a Butterworth filter is, let's take a 3-stage RC filter. If I have 3 poles at -1, gain versus frequency is, I start right here. It's going to be 1 over S plus 1 cubed. S goes to j omega, so this is the vector 1. This is the vector j omega. So this vector right here is j omega plus 1, or S plus 1. The gain is 1 divided by that distance cubed. So if I plot gain sideways, the gain's the maximum at s equals 0. As I move away, the gain drops off, and I get that kind of response. Now, if I were to take the poles and move them around the unit circle, I'll take 2 of the poles and move them, like to here and here. What's going to happen is I now have a resonance at s equals 0, close to this pole. I now have a second resonance. So the gain goes down, and I have second resonance. Then the gain drops off. And likewise, complex conjugate. As I move this pole, move the angle of the pole, the gain at these points starts to increase. A Butterworth filter is how far out can I move it until the gain never goes above 1. And there is only one answer. Turns out it's symmetric. The Butterworth filter, the amplitude of all the poles is 1. This is for a corner at 1. The angle between poles is, for 3 poles, 180 over 3. So this is 60 degrees. This is 60 degrees. So it's actually really easy to calculate. For 3 poles, I have a pole at -1, plus 16 minus 60 degrees. If I have 5 poles, I'm just going to do odd numbers right now. We'll do even numbers later. Erase all this. Erase. Okay, so suppose I want to do 5 poles. The amplitude of the pole is all the same. Here the corner's at 1. And I'll scatter 5 poles in the left half plane. There's 3, 4, 5. The angle between the poles is 180 over 5. So all these angles are the same. 180 over 5 is 36 degrees. So this is 36 degrees. That's 36 degrees. And it gives you these poles. So again, the pole location is really easy to calculate. If you have an even number of poles, it's a little bit odd. So let's take 4. If I have 4 poles, I scatter 4 poles, left half plane. 180 over 4 is 45 degrees. So this angle's 45, that angle's 45, that angle's 45. The oddity is that this is 45 degrees. Half is above, half is below. So this angle right here is actually 22.5 degrees. That's this guy. Plus another 45 gives you 67.5 degrees. So that's kind of how you find the pole locations for Butterworth filter. The nice thing about them is I don't need Wikipedia. I don't need a table. You can calculate them pretty easy. And again, a 5th order Butterworth filter looks like this. I've got 5 poles on the inner circle. If I want the corner to be 10 radians per second, I place 5 poles on a circle with a radius of 10. 20 radians per second, the circle's at 20, and so on. So this number right here is the amplitude of the pole. That's your corner frequency. And the poles are 36 degrees apart. So again, this is 36 degrees. That's 36 degrees. And the numerator is whatever it takes to make the gain 1. That's the form of the Butterworth filter. Butterworth filters behave much, much better than RC filters. Again, for an RC filter, the gain started at 1. It was 0.7 per single pole. For 5 poles, it was 0.7 to the 5th power, which is right around here. Butterworth filter, the gain is fairly flat and then drops off. Again, designed for the corner at 10 radians per second. So this is what the gain should be. Gain should be 1 out of 10 radians per second, then flat. It does pretty well out to about 6 or 7 radians per second, then the gain drops off. Much better than an RC filter, but to implement it, you need a different circuit, which we've covered, so it's not that big of a deal. You just need an op-amp circuit to build it. That's a Butterworth filter. To implement a Butterworth filter, again, what I would do is I'd factor it into 3 sections. Here's a real pole. There's a complex conjugate pair. There's another complex conjugate pair. The real pole I can do with an RC filter, so make that 10K, 10 microfarads. One of our RC is 10. This section I implement as a second order low pass filter. The corner's at 10, 1 over RC 10, and this sets the angle to 36 degrees. Then this is a second two-stage or second order low-pass filter. 1 over RC is 10, and this sets the angle at 72 degrees. So that would be a fifth order Butterworth low-pass filter. For seventh order, you add another stage like this. Ninth order, add another stage like that. Pretty much I use odd number of poles for my filters just because if I do an even number, I don't need this RC, and that's not that hard to build. So I might as well make it a fifth order filter, an odd number. If you throw that circuit in Circuit Lab and then sweep the gain versus frequency, this is what you see. Again, the gain is fairly flat because this is a corner at 10 readings per second. That's what it was. 10 readings per second is 1.6 hertz, which is why I was confused. 1.6 hertz is about here. So the gain is flat, fairly flat out to the corner frequency, 1.6 hertz, or 10 readings per second. Then the gain is supposed to drop off. Oh, drop off there 0. Not exactly drop off, but that's the best you can do. If you constrain yourself to having n poles and the resonance cannot be bigger than 1, this right here can never go above 1. That's a Butterworth filter. A type 1 Chebyshev filter is really similar to a Butterworth filter. Get up and look at a third order filter, RC filter with a corner at 1 reading per second. I've got 3 poles right here. Butterworth filter, I take 2 poles and slide them out to 60 degrees and minus 60, and that's a Butterworth filter. Chebyshev filter, you're allowed to have a slight resonance. And so what happens is the poles wind up being on an ellipse. It looks kind of like this. So this pole slides in, this pole goes out slightly, and this pole goes out slightly. It's a complex conjugate. The net result is the gain versus frequency has a slight resonance, another resonance. There's a little bit of ripple in it like this. And the gain can be bigger than 1. That's the difference between a Chebyshev and a Butterworth filter. Butterworth filter, the resonance can never be bigger than 1. Chebyshev, you're allowed to have the gain a little bit bigger than 1. The problem with Chebyshev filters is there's an infinite number of them. It depends upon how much of a resonance you allow, which makes them tough on midterms. The table right here, I said that the resonance is at most 0.02. So the biggest the gain can be is 1.02. Go to Wikipedia, or this actually came from Scilab. Tell it the corner, 1 rating per second, how much of a ripple, how many poles you want, and it drops out these guys. So to design a Chebyshev filter, you need a table. Here's a table for you, or Wikipedia, or Scilab, somewhere to tell you where the poles are. It's not that easy to calculate. But there's only one Chebyshev filter once you specify how much resonance you're allowed. And this is for corner at 1. If I want the corner to be 10 readings per second, just multiply the amplitudes by 10. Okay, like I mentioned, a Butterworth filter, the poles are on the unit circle with a radius of 10. A Chebyshev filter, the poles wind up on an ellipse. And again, the angle between the poles isn't quite as nice as it was with the Butterworth filter. It's wherever it is. And if you plot the gain versus frequency, looks like I draw the gain sideways, you can kind of see what the gain is going to look like. At this point at DC, I'm close to this pole, I get a resonance. Then I move away from the pole, the gain drops. Then at this pole, I had another resonance, and the gain drops. Then I had another resonance, and the gain drops. And the resonances keep on getting tighter and tighter, because the real part gets smaller and smaller. That sets the bandwidth. If you plot the gain versus frequency, here's what a Chebyshev filter looks like. This is a second order Chebyshev, third order, fourth order, fifth order. And notice the gain's really flat. It's got a little bit of ripple here. There's the pole on the real axis. Here's the first complex pole. There's the second complex pole. Then the gain drops off as 1 over frequency to the 5th power, since I have 5 poles. Chebyshev filters are much better than Butterworth, way, way, way better than RC. The gain is almost flat out to your corner at 10 radians per second, and it doesn't drop off like a rock, but it's dropping off as 1 over frequency to the 5th power. By 15 radians per second, the gain is less than 10%. They're actually really good filters. To implement a Chebyshev filter, it's actually not any harder to implement a Chebyshev than a Butterworth. I've got a real pole, 2 sets of complex poles, so I have an RC filter, 2 second-order low-pass filters, just like a Butterworth. The difference is the amplitude of the pole is different for each one. So for a Butterworth filter, I always had the same RC combination. This one, they're different. The first 1 over RC is 4.8. That's this guy. The second 1 over RC is 7.6. The third 1 over RC is 10.6. The angle, the first angle is 59 degrees, so this sets, pick K to set the angle to 59 degrees. This one, the angle is 82 degrees, so pick K to make the gain angle 82 degrees, and you have a 5th order Chebyshev filter. For my money, there's not a whole lot of difference in implementation between a Chebyshev and a Butterworth, but Chebyshev works better. So, given a choice, I would use the Chebyshev filter. And circuit lab. If you build that circuit and then do a frequency sweep, you see it's almost right. It gains fairly flat, there's your resonances and drops off. This is dipping a little bit. The reason it's dipping is there's some loading effect. If I made that a 1K, 200 microfarads, the loading over here would be less. Or if I used a 3rd op amp to implement this, the real pole, then it would be dead on. But that kind of verifies that, yep, that's the way implemented is about right. This is the output Y, and this is the output of the first op amp, which I don't really care that much about. So that's a Chebyshev filter. Third or fourth type of filter is an elliptic filter. An elliptic filter is the closest approximation to an ideal low-pass filter, subject to there being n poles up to n zeros. The maximum gain cannot exceed 1 plus epsilon 1, and the maximum band reject cannot exceed epsilon 2. So what this kind of says is if I want to build a filter at 1 radian per second, I'm allowed, so if this is 1, I'm allowed a little bit of a resonance. So this can go actually a bit above 1 by epsilon 1, say like 1.02. At the band reject region, like if I take this guy right here, omega equals 3, at 3 radians per second, the gain cannot exceed some other number. I think the number it shows is 0.001. So come up with a filter that wiggles around, doesn't go above 1 plus 1.02, and then drops over here. That's an elliptic filter. What the zeros do is this forces the gain at 9.9 radians per second to 0. For this case, I have 4 zeros. That forces the gain at 3.2 radians per second to 0, and at 7.7 radians per second to 0. Now the good thing about an elliptic filter is the zeros make the gain drop off faster. The bad thing about an elliptic filter is I've got 4 poles, 4 zeros. The high frequency gain doesn't go to 0. But the argument behind an elliptic filter is if the high frequency gain is less than 0.01, I don't really care how much less than 0.01 it is. It's small enough. So that's kind of the idea. If you specify the pass band, the reject band, as you take the reject band and slide it in, it gets tighter and tighter. It gets harder and harder to build the filter. So I get more poles and more zeros. And if I make the reject only 30% higher, I wind up with 7 poles and 6 zeros. That's an elliptic filter. If you plot the gain versus frequency for a 5th order elliptic filter, here's what it looks like. Again, the gain was 0. That was this guy. At 1.8 and 2.4 radians per second. Scaling it by 10, it'll be at 18 and 24 radians per second. This is on an absolute scale rather than a log scale, so it's kind of hard to tell. That actually goes to 0. And that's the advantage of the elliptic filter. Instead of just dropping off like a Butterworth or Chebyshev, I nail it down to 0 right here. Keeps it kind of small. And it's actually a pretty impressive filter. The gain is about 1 out to 1 rating per second. Then it drops off really fast. The problem with elliptic filters is, well, we don't really know a circuit that actually build it. There are circuits that do that, but we haven't covered them. If you program this in software, then the software doesn't really care. Poles, zeros, real, complex, it's all the same. So these are actually easier to implement in software than hardware, but that's a different class. One thing to note about these filters. The filters that we designed had a corner at 10 radians per second. Suppose I want to redesign it so the corner is at 100 Hertz. Well, one trick to doing that is as follows. Capacitors are integrators. If I integrate a circuit 10 times faster, or if I make the capacitors 10 times smaller, I will integrate 10 times faster and respond to frequencies that are 10 times higher. So basically, all I have to do is scale the capacitors, take the previous design, wherever it was, take this previous design. This has a corner at 10 radians per second. If I divide by 100, the corner is now 1,000 radians per second. So just take every capacitor, scale them by the same amount. Everybody's integrating 100 times faster. Everything is responding to frequencies 100 times higher. If you do that, the magnitude of the poles, relative magnitude stays the same, the angle stays the same. All that changes is the amplitude. It becomes 100 times bigger. So that's oftentimes a trick that's used in circuit design. You design for a nice number, like 1 Hertz or 1 rating per second. I can then do any frequency just by scaling the capacitors. So take that previous design, leave everything alone, just change the capacitors. Make them 62.8 times smaller, and now the corner is at 100 Hertz rather than 10 radians per second. That's just the difference between 100 Hertz and 10 radians per second. 100 Hertz times 2 pi is 628, 62.8 times the frequency. And if you simulate that in Circuit Lab, sure enough, at 100 Hertz, the gain is fairly flat out to 100, then drops off. So really, if you just design one circuit, you've designed them all. Just scale the capacitors to get a different value. For filters, filters are really useful. So not surprisingly, you can buy filters on a chip. If you go to Chebychev, the electrical engineer's favorite playground, you can buy over 1,000 filters on a chip. And you kind of see on the left, I've got my bandpass, Bessel low pass. You can get Chebyshev filters, also known as a Bessel filter, Butterworth filters, lots of different types. I can have up to 7 filters on a chip. I can have up to 10th order filter on a chip. Now that's pretty impressive. I wouldn't want to build a 10th order filter using op amps and capacitors. I can just buy one on a chip. Unless you're taking electronics and you want to demonstrate the ability to build filters, then you build it. After electronics, just buy the chip. Kind of one thing you got to realize, engineering time is like $100 an hour. If you buy a chip and it saves you, it's a $2 chip, saves you 2 minutes, it's worth just buying the chip. Don't waste your time building it. Just because you can doesn't mean you should. Example filter is the LTC 1164. This is an 8th order elliptic filter on a chip. The corner frequency is set by a clock input, and the gain versus frequency is really impressive. The gain is flat at your corner, and then it just drops. So these are the zeros that you're seeing. This is on a log scale. The way it works, this is actually a microprocessor in analog electronics. I can scale the frequency by changing all the capacitors. With a microprocessor, a digital filter, if I double the clock frequency, I double how fast the program executes. I double the bandwidth. So by setting the clock, changing the clock frequency, I can set the clock to change the corner frequency of the filter. So this is a circuit that just has, you input the clock and that tells you the corner. On other chips, you just add a capacitor. That sets the clock frequency, that sets the corner frequency. And they do that because it's a lot easier writing code than building an 8th order op-amp circuit. An 8th order op-amp circuit would need 8 capacitors that you have to add. This chip only needs 1 capacitor. And from an input-output standpoint, anything I can do in hardware, I can do in software, vice versa. From an input-output standpoint, I don't really care how you implement the filter. I just want it to work. And so this, is it analog? Is it digital? Yeah, I don't really know. I don't really care. Actually, I do know. There's only one clock input that tells you it's a microprocessor. But from an I/O standpoint, doesn't matter. Last thing to cover is find the R's and C's to implement this filter. And I'll give you a couple minutes to think about that, or you can pause the video. Okay, picking up, I'll split this into 2 halves. Again, the numerator I don't care about, I'll ignore that for now. This will go to that half, this will go to this half. The resistors, capacitors, I've got 2 degrees of freedom, 1 constraint, so somebody's arbitrary. So let's make this 100K. I want 1 over RC to be 0.72. So 0.72 times 100K is 13.8 microfarads. Over here, 1 over RC is 1.1. 1.11 times 100K. C is 9.09 microfarads. Likewise over here, that's for both of them. To find R1, that's the angle. 3 minus K is 2 times the cosine of the angle, 38.5 degrees. Solving for K, 38.5 cosine, 2 times 3 minus, K is 1.3, 1.435. Over here, 3 minus K is 2 cosine, and this is at 77.8 degrees. .8 cosine 2 times 3 minus 2.577. K is 1 plus the resistor ratio. So for gain of 1.43, this becomes 0.43 times 100K, 43K. And this becomes 157.7K. And that circuit will implement a 4th order filter. This one's actually a Chebyshev filter. I know that because the poles aren't the same amplitude and the angles aren't nice. Numbers like 22.5, 67.5 degrees. And that's just what we did. As a sidelight, the DC gain is supposed to be 1. This has a DC gain of 1.43 times 2.57. What I would do is just say the output isn't Y, it's 3.68 times Y. The reason being is presumably the rest of the circuit needs to amplify your input somewhat. Again, if you have a sensor, audio, whatever, you need to amplify it typically. This filter provides a gain of 3.68 free of charge, so you might as well use it and let the rest of the amplifier handle the rest of the gain. So in summary, if you're willing to use complex poles, you can do much better than an RC filter. Butterworth filter is one option. It has a maximum gain of 1. It looks like this. It's fairly easy to design. A Chebyshev filter is another option. It has a slight resonance, a little bit of ripple. the gain is flatter out to the corner. And an elliptic filter is even better yet, but you need to use something that has zeros as well as poles. We know we can just do RC, Butterworth, and Chebyshev. The Chebyshev is a little bit trickier to design, but if you have a lookup table, you can figure out where the poles are. And if you want to change the corner frequency, that's also really easy. Design your Chebyshev filter for a corner at 1, or in this case 10 radians per second. If you want to change the corner, just scale the capacitors. That's lecture number 9 for ECE 321, Analog Electronics.